So with this weak acid and strong base, and we know it's a weak acid because HF is not one of those six. Those six are HCl, HBr, HI, HNO3, H2SO4, and HClO4. When we do it the same way. We do a double switch. And so we get H2O liquid, and we get NaF. And that would be aqueous. But the HF, since it's weak, has to stay together, doesn't separate. The Na does, OH does. You get our H2O. Na is plus, and F is minus, because if we look on our solubility table, anything with Na in it is going to be extremely soluble. So then we get rid of Na, that's our spectator ion. It's still there, it's just not part of the reaction. Part of the reaction is going to be HF plus OH minus gives you H2O plus F minus.
So your net reaction thing, where
Yeah.
you have just like H2O plus F minus, that kind of like shows you what you get if you like. It's like the sodium is just kind of like an added thing in there, right? It's just a way to get
It's a way to get the ions
the hydroxide in.
right to get it dissolved.
So if you just had like OH somehow and you mixed it with HF, it'd do the same thing as if you mixed
Right.
NaOH.
I don't know how you get that because usually you have to have But yeah, true.
So that Na isn't part of the reaction; it just breaks apart and sits there, and then it bonds to the others that are free.
It doesn't do anything.
Well,
It's pretty much
So it's basically third wheel.
third
It's
wheel.
there. It's just at the party.
but it forms sodium chloride. Doesn't it?
Really, it doesn't.
Oh, it doesn't.
Well,
And that's why this last reaction is what you should really look at, because Na doesn't react with fluorine. We just write it on the right side because if they would go together, they would go together that way. But when you look at them in the solution, they're separate and they're floating around, separate of one another. But that's why this is a lot more important than the top one, because we're getting rid of those ions. They're not involved. Okay, so that's how you do strong acid, strong base, and also weak acid, strong base. We're not going to do a weak base because we're not going to get to that point to where we have to do it. Any questions you have with that? All right?
Would this be like a violent reaction, or just?
What's that?
Would this be kind of a violent reaction?
No. No, I mean it's all based upon how strong your solutions are. Most of these we do in labs are pretty weak. Yep, pretty weak.
Would you still write like aqueous and everything with the...
At the end, you probably should put aqueous. If they're an ion floating around, at the very end, I didn't do that, but you should put aqueous on those at the end. You need to identify everything at the end. I don't do it in the middle just because I'm using that method in which to see which ones where the spectators they're out of the scenario. All right. The next part is the actual calculation process, and it's real similar to what we did on Thursday when we set up our ICE. Now, I'm not going to set these up as ICE. Okay? I'm not going to do that. At least initially, I'm not going to. Okay. So, we know that we take an acid and base, they'll neutralize one another. Alright? And on this one, I'm going to leave it in the form of a formula equation. I'm not going to go down to the net ionic. I'm going to leave it in the formula equation because that's going to allow me to do my calculation. So don't, if you're asked for certain concentrations, and it's asking you to do a problem that, just leave it in the formula equation like this. You would just go KOH plus your HBr And then you go H2O plus your KBr. And leave it in this form, okay? You don't have to take it out of this form. So, what I'm going to do is, I'm going to go ahead and do a long version, and then maybe the next one I'll show ice. I'm not sure on AP tests how they look at ICE. I think they, as long as you're descriptive and you're identifying your concentrations in that, I think you're okay. And they'll give you credit for that if you're showing that and come up with the right answers. But what I'm going to do is I'm going to find the concentration of HBr. So I want to find at the end here, I want to find moles over liters of HBr. Okay, at the end. So I'm going to go ahead and start out with the 0.25 molar. That'd be moles over liters. I always like to use moles over liters, because molarity doesn't cancel out volume or moles. It just is molarity. So moles over liters, and that's going to be of KOH. What do you think the next thing I'm going to do to figure out my molarity of HBr? What do you think the next thing I would do? So next step, what should I cancel out?
Times it by the liters of
0.03 liters.
0.03 liters. Very good. So 0.03 liters cancel out. Now I have moles of KOH. Now I want to find moles of what? Okay, HBr. So what I'm going to do is say for every 1 mole of KOH, I have 1 mole of HBr. So now I have moles of HBr.
Are there going to be somewhere we have to balance the equation too?
Yes,
Okay.
it's the next one. Well, this one's balanced,
Well, yeah.
but yeah, that'll be the next one.
Yeah.
And that's why you need to set it up this way so that you can, yep. So now I got moles of HBr. Now all I have to do to get moles over liters is to put what down here? 0.05. Now I got moles of HBr over liters of HBr, and that's molarity. And that would give me my answer. Okay? Questions on that? I just have one more of these to do where Jared had brought up. If they don't, or they're not 1-to-1 ratio, but you do it the same way. It's not any different. It's just that when you set up your mole ratio, it's like when we do stoichiometry. We've done it in the past. So the concentration is 0.15 molarity. Molarity. Any questions with that? Okay, what I'd like you to do on your own is we're going to get rid of this part here. I'm not going to do this today. So go ahead and write out the reaction. We have what we call a diprotic acid. If that's the first you've heard of that. Di means 2. Protic would be the hydrogen is really a proton because it doesn't have an electron and it doesn't have a neutron. So hydrogen positive ion is a proton. Okay? So it has a hydrogen ion, which is basically a proton, so they call it diprotic acid. And when you have a diprotic acid, it takes, and you have a base with just 1 hydroxide, then you know you're going to form 2 waters out of the deal. But if you set that up and do it anyway, you're going to see that, you know, it's going to be a 2-to-1 ratio that you're going to have. So you're going to have twice the amount of base with a diprotic acid than you will with the monoprotic acid, the same concentration. Because it's going to take double the OHs to balance out the A's pluses on there. So go ahead and set up your problem and see what you come up with as an answer. This one's wanting to know the concentration of H2SO4. So go ahead and solve for the concentration of H2SO4 and see what you come up with. So the concentration would be 0.0. Yeah, 0.040. Okay, questions?
How did you get the .006.764?
That's points.
Milliliters.
That's the liters.
That's liters. You can't.
That's liters?
Yeah.
Okay, that makes sense then, yeah. I was like, I have no idea where you got
First thing about those.
If you didn't get it the first time, which I think you would have. I hope. Okay, so we have strong acids and strong bases. HCl is a strong acid. The other strong acids would be HNO3, HBr, HCl, which is that one, HI, H2SO4, and HClO4. Strong acids break apart completely, but we'll do the reaction. So you have H2O liquid with a strong acid, strong base, and then you have NaCl is the other combination, aqueous. And they break it down, everything breaks apart, H plus, Cl minus, Na plus, OH minus. Water stays together though, doesn't break apart, it's a liquid, and then we have Na, breaks apart. Solubility rules said anything with sodium in it, it's going to break apart completely. So we have Na plus and Cl minus. So this is the complete ionic.
Yeah.
Then we get rid of our spectator ions, that would be Na and Cl. So then what we're left with is this H plus OH minus gives you H2O, and this is always the way you write strong acid, strong base reactions. That's all you have involved in strong acid, strong base. But in weak acids, the one we did earlier, the HF stays together all the way down. And it doesn't break apart because it's weak. So this would be what the difference is here. This one is weak. And the one that was strong we just did. Is H plus OH minus gives you H2O.